All right, let's get started with Lesson 9, Properties of Liquids. Now, in this lecture video, we're going to look at three different properties of liquids. We're going to focus on viscosity, we're going to focus on surface tension, and capillary action. Now, most properties of liquids are influenced by their intermolecular forces, as much as we saw in our last lesson, Lesson 8, that the boiling points of molecules and their melting points are very much governed or dictated by the intermolecular forces between them. And we'll see that with these properties as well. Alright, so let's start out with viscosity. Viscosity, by definition, is the resistance of a liquid to flow. The greater a liquid's viscosity, the more slowly it flows. Kind of like this honey here. It's a very viscous substance, and so it has a quite slow flow to it. The viscosity overall is dependent on the liquid's intermolecular forces between the molecules and on the shape and flexibility of the molecules, such that they tend to become entangled. All right, so let's first look at the intermolecular forces. Obviously, the stronger the intermolecular forces, the more intermolecular forces that exist, the more viscous the liquid should be. Shape and flexibility. What do we mean by that? Well, think of this. Think of an entangled spaghetti noodles. If you take spaghetti and you entangle them together, it creates a stronger collective bonding of those spaghetti noodles. So same thing with molecules. If you take molecules and they have some flexibility to entangle themselves, then that's going to create a higher viscosity, or the molecule is going to be more viscous, and the liquid will not flow as easily as it would if it doesn't entangle. All right. So intermolecular forces, shape, and flexibility, and then the last thing is the viscosity is really temperature dependent. All right. The higher the temperature, the more viscous the substance, the less viscous the substance should be. It should be able to flow much easier as the temperature goes up. And you think of this. Think of logic here. As I increase the temperature, I add more energy to the molecules, and so the intermolecular forces begin to be broken up. And so if the intermolecular forces are broken, then typically the molecules are going to have less viscosity, and they're going to flow much easier. All right, so think of that with viscosity. All right, a way to measure viscosity is to use a steel ball usually, and in this case we have 4 different liquids, and they're probably oils of some sort, and each one of them is in a test tube, and we add a steel ball to those test tubes, and the faster the ball flows through the liquid means the less viscous it is. So for instance, this last one here, because the ball seems to be having trouble getting through, this one right here, it tells us that this liquid right here has more viscosity. It's more viscous. The intermolecular forces are probably stronger in this one, or the molecules can entangle much better. Obviously, the first one, the steel ball is moving much faster through it, therefore it's not as viscous. The intermolecular forces are weaker, or there's not as much entangling going on. And of course, this is all assuming this experiment is taking place at the same temperature. You increase the temperature, and you should cause the steel ball to move faster through the liquids. All right, so there's some things about viscosity. Let's go to surface tension now. So I have a diagram of some molecules that are in the liquid state here. Now, molecules that are in the interior. All right, so let me highlight that. These molecules right here that are in the interior of the liquid. They're going to be attracted to one another by intermolecular forces in this liquid. All right. Now, The intermolecular forces, though, is going to be balanced out because there's going to be a pulling of these molecules basically in opposite directions. So, for instance, the one that's highlighted here, which is right here, this molecule here, it's going to have a push and a pull in all directions outward, okay? And those directions, the push and pull is going to be pretty even. Therefore, there's not going to be any net movement of this molecule. It's going to feel no net pull, essentially. No net pull in any direction, all right? However, on the surface, molecules that exist on the surface is represented by this molecule here. You're going to have molecules that are pushing and pulling here, and pushing and pulling, pushing and pulling, pushing and pulling. But there's no molecules on the surface pushing and pulling. All right, so this is going to create a different situation for molecules on the surface in the liquid state than in the interior of the liquid. So essentially what's going to happen is on the surface molecules, there is no upward force to cancel out the downward force. So you can see the downward force is going in this direction due to the pull of these molecules here. But there's no molecules up above in this area to push those surface molecules up. Okay, there's just no attraction there. That's going to have a big effect. Okay, this means that the surface molecules feel a net downward force. Okay, so let me erase all of this. So essentially what we mean then is that there's going to be a net downward force going in this direction. All right, and that net downward force then is going to create a very tightly packed molecules at the surface. All right, these molecules are going to be tightly held together or packed very closely together. And this tight packing of these molecules at the surface, it creates what is known as surface tension. All right, and the more tightly packed the molecules are, the greater the surface tension. So what's going to influence that then, of course, is going to be the intermolecular forces, because the stronger that downward pull is at the surface, the bigger this downward pull, then the stronger the surface tension will be. And so, for instance, molecules that are liquid, that are hydrogen bonding molecules, they're going to have a much higher surface tension because that downward pull is going to be so much greater than, say, molecules that are just using dispersion forces. All right, so that's kind of the idea of surface tension here. Now, again, contrast that to the interior molecules. You have an upward pull, a downward pull, side-to-side pull. So this molecule is essentially not moving anywhere, going nowhere. And so it doesn't create any surface tension like you do with those surface molecules. Now, there's a lot of implications to this, such as water. Water itself, because it hydrogen bonds, has a very high surface tension. And so certain organisms can even walk on water because that surface tension is so high. You can even put a paper clip and put it on top of the liquid, and it should hold the paper clip. It should not sink if you do it just right because of that high surface tension on water. Okay? So surface tension and intermolecular forces are related. All right, let's look at the last one, capillary action. Capillary action, by definition, is when a liquid, such as water, rises in a narrow tube, pulling the liquid up the tube until the force of gravity on the liquid balances the adhesive and cohesive forces. All right, so that's what capillary action is. So what is cohesive and adhesive forces? Well, cohesive forces are it's just a general word, and it just means that you have intermolecular forces that bind to other molecules. Whereas adhesive forces are intermolecular forces that bind a molecule or a substance to the surface of something. Okay? So when we're saying that something is adhesive, it just means that a molecule is going to bind to the surface, some surface, through intermolecular forces. All right? So let's look at some effects of this, okay? Cohesion and adhesive forces. If the adhesive forces are stronger than the cohesive forces, then a liquid will simply form a meniscus that is concaved. All right, so something like in this general water is going to form a concave meniscus. It's going to be, oops, that's kind of bad. It's going to be going up like so. Just not being able to draw very well. There we go. It's concaved up. Okay. What this means then is that the adhesive forces are stronger than the cohesive forces. In other words, the liquid is more attractive to the surface that it's in contact with than it is to itself. So water molecules, even though they hydrogen bond with each other, forming a very strong cohesive forces, the bonding between the glass and the water molecules is much stronger, therefore we get a concave meniscus. Now let's contrast that to mercury. Now mercury is going to have stronger cohesive forces than it has adhesive forces. In other words, what we're saying is that mercury has a stronger attraction for itself than it does to the glass. And so as a result, it's going to form a convex. So it's going to be bowed down instead of up like we see with water. So like this, bowing down. Okay? So let's kind of draw some diagrams here in your notes of this situation. So let's say we have glass, and the glass we're just going to represent by some bonding here, just some generic bonding to create this glass. You're going to have some bonding here, and bonding here, and so forth. So this essentially is the glass and all the bonding going on. Now let's compare that to like water then. Now water has a bend structure and is a polar molecule, has a negative pole there, a positive and a positive pole there, okay? So you're going to have some adhesion forces between the water molecule and the glass. And we're also going to have some cohesive forces. And that's negative, so we're going to have some cohesive forces. Here's the hydrogen bonding. But that hydrogen bonding is also the cohesive. Okay, cohesive versus the adhesive. Okay, and all we're saying here is that these adhesive forces between the glass and the water are much stronger than the cohesive forces between the two water molecules. So therefore, that's going to cause the concave meniscus bowing up. Now, when this occurs, when the cohesive forces are not as strong as the adhesive forces, then liquids will rise in those narrow tubes to form capillary action will occur. And so water is very good at capillary action. And we see this a lot with trees. For instance, water is found in the ground, and so the small veins within the trees is going to cause the water to rise through capillary action up to the leaves of the trees where it can be used for photosynthesis. And that just says that the adhesive forces in the trees between the water and the tree veins are much stronger than the actual cohesive forces between the water molecules. Okay, and so we kind of see that idea. Although because the cohesive forces are still there, therefore we get a chain of water molecules that go up the tree because they're all hydrogen bonded together, creating a very strong situation. All right, so let's contrast that over here to the mercury. So the mercury, we get, here's the glass again. Here's our bonding. Form all these bonds, the glass. Alright, so this is just kind of our glass again. Alright, so here's the glass. Oops. I lost my diagram. Shoot. Okay, let's restart that again. Alright, so you just put this in your notes, this diagram. So here's my glass again. Here's the bonding. It takes place in the glass. So here's the glass. Right, now as far as the mercury goes, the mercury, of course, is going to have metallic bonding. And you know that metallic bonds are very strong compared to hydrogen bonds. So what's going to happen is there literally is going to be a stronger cohesive forces. So the forces here, these cohesive forces that these metallic bonds make, are going to be stronger than the bonds between the glass. And so therefore there's going to be the bowing that occurs going down, that convex bowing in the meniscus of the mercury. Okay, so that's kind of what we're trying to look at here. So that's it for this lecture video. If you have any concerns or questions, please let me know before you take the quiz. Other than that, we'll take the quiz over these properties of liquids, and that is it for now.